Have you ever had that moment where you're trying to understand something, right? And the person explaining it just keeps going and going, adding all these details. You kind of get lost in the weeds and you think, like, what's the main point here?
It's like they're giving you a novel when all you need is the Spark Notes version.
Haha, exactly. And sometimes it feels like AI language models are doing the same thing. They're capable of these incredible reasoning feats, but they often take this really long, winding path to get to the answer.
And it's that very problem that's driving some really interesting new research. Like, how do we get AI to think more efficiently, more like an expert who cuts to the chase and gets right to the core idea?
That's what we're diving into today, a new approach called Sketch of Thought, or SOC. It's all about getting AI to reason in a more concise, focused way. And for you, our listener, that means understanding complex topics without getting bogged down in unnecessary detail.
It's about getting to that ha moment faster, basically.
Right. So in this deep dive, we're going to explore how SOT takes inspiration from human cognition, how we efficiently process information to make AI reasoning more streamlined and academically rigorous.
Because let's be honest, a lot of us are busy. We want the core insights, the essence of the knowledge, without having to wade through a sea of words.
Absolutely. So to kick things off, let's set the stage. Why is this push for conciseness in AI reasoning so important?
Well, one of the biggest breakthroughs in AI reasoning has been chain of thought prompting, or COT, where you basically ask the AI to show its work step by step.
Right, like those thought bubbles in a comic strip showing how a character solves a problem.
Exactly. But as groundbreaking as GOT has been, it has a big limitation. Those thought steps, they can get really, really verbose.
So you end up with this long chain of explanations that, while they might be accurate, can be really inefficient.
And in the world of AI, inefficiency equals higher computational costs. More words, or tokens as they're called, mean more processing power and time required.
Not ideal when you're dealing with real-world applications, especially in resource-constrained environments, like running AI on your phone or in time-sensitive situations.
Right, think about it. A brilliant AI that takes forever to process a request isn't very helpful in a fast-paced world. And researchers have actually put number to this. We've got studies from NIOB and colleagues this year, and Aurora and Zanet, also in 2025, really highlighting the token inefficiency of traditional COT.
Yeah, and it's not for lack of trying other methods. I mean, we've seen techniques like self-consistency, where the AI generates multiple reasoning paths to increase confidence in the answer.
Right, and then there's tree of thoughts and graph of thoughts, which allow for more complex explorations of a problem. But all of these methods, they often end up generating even more steps, which kind of exacerbates the whole token issue.
So SOT comes in and says, okay, let's rethink the whole reasoning process itself. Instead of tweaking the instructions we give the AI, SOT focuses on how the AI expresses its reasoning internally.
It's like giving the AI a whole new way of thinking, drawing inspiration from how humans think efficiently.
And the core inspiration, as the research paper clearly states, comes from this cognitive science concept of sketches.
Sketch.
Yeah, think about it. When you sketch something, you're capturing the essence, the key elements without all the fussy details, right?
Like a rough outline of a building, or maybe a quick diagram explaining a concept?
Exactly. It's about efficient representation of information. And so T aims to bring that same level of efficiency to AI reasoning. Instead of these long, flowing natural language explanations, it guides the models to express their thoughts in a more condensed, almost symbolic manner. And that's where these three cognitive inspired paradigms we mentioned earlier come in: conceptual chaining, chunked symbolism, and expert lexicons. Each one provides a unique pathway to more focused and, dare I say, more intellectually rigorous AI reasoning. Let's start with conceptual chaining.
This one's really fascinating because it taps directly into how our brains organize and retrieve information. It builds on ideas like the episodic buffer in our memory, where we temporarily link different bits of info, and the concept of associative memory networks, where one concept triggers another. Like if I say coffee, you might think morning or caffeine, right?
Yeah, our brains are constantly making these connections, creating these mental pathways between concepts.
Exactly. And conceptual chaining leverages that. It trains the AI to identify the key entities in a query and then express the reasoning as a concise path connecting those concepts. It's about establishing logical relationships with minimal verbalization,
Like a mental shortcut almost.
right? And the paper gives a really clear example for the question, what is the currency of Seoul? Conceptual chaining would reason like this: Seoul, South Korea, 1.
Wow, that's incredibly direct. It completely skips all the extra descriptive contexts.
And the research shows that this approach is particularly effective for things like common sense reasoning, multi-hop inference, where you have to connect multiple pieces of information, and factual recall. It makes sense because it's all about efficiently retrieving and connecting related knowledge.
Makes total sense. So let's move on to chunk symbolism, the second paradigm.
This one's all about working with numbers and symbols. It's rooted in this classic idea from cognitive psychology about the limits of our working memory.
Okay, I remember learning about this. It was George Miller's work, right? Something about how we can only hold a limited number of items in our short-term memory at once.
Yeah, like 7 plus or minus 2 is the magic number. But we get around that limitation by grouping things together into meaningful chunks. Like, think about how you remember a long phone number. You probably break it down into smaller segments.
Oh, yeah, definitely. I never thought about it that way. So chunk symbolism applies the same principle to AI reasoning, particularly for tasks that involve math or symbolic logic.
Precisely. Instead of explaining every single step of a calculation in lengthy natural language, it encourages the AI to represent the reasoning in a compact, structured format. Extract the key variables, present the equations clearly, and show the operations succinctly, almost like a mathematical shorthand.
I'm seeing the efficiency here, and the paper gives that great example with the car acceleration problem. Instead of a paragraph-long explanation, SOT with chunked symbolism just presents the essential elements. A equals 2.5 meters to T equals 10s, Y equals 15 meters, VF equals 15 plus 2.5 by 10, and VF equals 40 meters. It's all there, but without the need for a lot of verbal explanation.
And the key academic point here is that by structuring information into these chunks, the AI can handle complex reasoning tasks much more efficiently, especially when dealing with quantitative information.
And that brings us to the third paradigm, expert lexicons. This one seems particularly relevant to how we communicate and learn in specialized fields.
Absolutely. This one is inspired by the way experts in different domains use specialized language. Think about doctors, engineers, lawyers, scientists. They all have their own jargon, abbreviations, and notations that allow them to communicate complex ideas quickly and precisely with each other.
Right, it's like a shared shorthand that facilitates understanding among those in the know.
Exactly, and there's a lot of research supporting this. Work by Chi and others way back in the 80s showed that experts developed these sophisticated knowledge structures called schemas, which allow them to quickly recognize patterns and use domain-specific shortcuts.
So expert lexicons aims to give AI a similar capability.
Precisely. It encourages the AI to employ domain-specific abbreviations, notations, and symbols to condense its reasoning, particularly in technical or specialized areas.
So instead of spelling everything out in detail, it uses these efficient shortcuts, just like a human expert would. And the paper provides that striking example from the medical field with the patient who has a STEMI, right, and is receiving monotherapy but is allergic to aspirin. So T using expert lexicons reasons, STEMI, ST elevation I, MONA, morphine, O2, nitrates, aspirin, so aspirin MONA. It's using those established medical abbreviations to get right to the heart of the clinical issue.
And another example is the way SATI decodes the scientific designation of the interstellar object Oumuamua, breaking down 1I 2017 U1 into its constituent parts based on the International Astronomical Union's naming conventions. It showcases how specialized knowledge enables incredibly concise reasoning.
Wow, these three paradigms offer such a cool and diverse set of tools for efficient reasoning. But how does Sati actually decide which one to use for your given query?
That's where the magic of adaptive paradigm selection comes in. So ETI incorporates a lightweight router model that acts like an intelligent switchboard, analyzing each incoming query to determine which paradigm is the best fit for the task.
So it's like a little AI reasoning strategist figuring out the most efficient approach based on the question at hand.
Right. And it does this by looking for certain linguistic clues. For example, the presence of mathematical symbols might signal that chunked symbolism is the way to go. If the query involves multi-hop reasoning or general knowledge, conceptual chaining might be a better fit. And if it detects domain-specific terminology, it might point to expert lexicons as the most appropriate choice.
It's like a super smart detective analyzing the language to predict the best course of action. And this router model, the paper mentions it's based on Distilbert. Any particular reason for choosing that?
Yeah, Distilbert is a smaller and more computationally efficient version of the larger BERT language model. They chose it specifically because it offers a good balance between accurately understanding the nuances of the query and minimizing computational overhead. You don't want the paradigm selection process itself to become a bottleneck.
That makes perfect sense. And it was trained using GPT-4a on labeled data to learn which paradigm works best for different types of questions, right?
Exactly. So it's not just randomly applying these paradigms, it's a dynamic system that intelligently adapts its reasoning strategy specific demands of the task at hand.
And the big question, of course, is does it actually work?
Well, the results are quite impressive. The researchers evaluated SUTI across 15 different datasets, covering a wide range of reasoning challenges using the Q-Quen 2.5 family of models.
So they really put it through its paces.
They did, and the key finding is that SOTI achieved significant token reductions. We're talking 71 to 76% on average, with a remarkably small impact on accuracy. Across all these different models, they only saw a decrease of less than 1% in most cases.
So huge efficiency gains without sacrificing accuracy? That's impressive. And, I was looking at their figure 1, and it really highlights just how consistent those token reductions were.
Yeah, it's pretty compelling. And what's particularly interesting, at least from a research perspective, is that in some domains, SOTI actually improved accuracy while reducing token usage.
Really? In which areas?
Well, for example, in mathematical reasoning, they saw token reductions of about 60%, but they also observed a slight increase in accuracy with the larger 32 billion parameter model. This really suggests that chunk symbolism is particularly effective for quantitative problem solving.
Makes sense given how focused it is on the core elements of mathematical reasoning.
Right. And it wasn't just limited to math. For common sense and scientific reasoning, they saw even bigger token reductions, like 77 to 85%, again with minimal impact on accuracy. It seems that in domains where concepts are well defined, the concise language fostered by SUTI really shines.
And what about multi-hop reasoning, where the AI has to connect multiple pieces of information to reach a conclusion?
That's one of the most interesting findings, I think. In those tasks, SOTI consistently led to accuracy gains, even though it was using fewer tokens. They saw improvements ranging from 0.44 to 2.45%, despite token reductions of 67 to 72%. The researchers think that the conciseness of SOTI might actually help the AI focus on the essential inferential links without getting bogged down in unnecessary details.
It's almost like the verbosity of traditional SOT can sometimes obscure those core logical connections.
Yeah, it's an intriguing possibility. Now, beyond just English, they also tested SOTI in multilingual and multimodal contexts.
So not just limited to one language, that's a great sign of its potential.
Exactly. In their experiments with Korean, Italian, and German, they achieved about an 85% token reduction with minimal impact on accuracy. This suggests that the fundamental principles of efficient reasoning that SOTI utilizes are not language-specific.
That's really exciting. And what about multimodal reasoning?
Well, they did some experiments with the Science QA dataset, which requires reasoning over both text and images. And there, too, they saw impressive results, achieving over 81% token reduction.
Wow. So it goes beyond purely textual tasks, which opens up a lot of possibilities. And they also explored combining SOT with self-consistency, right?
They did, and their findings indicate that this combination actually amplifies the efficiency gains. You get the benefits of generating multiple reasoning paths for increased confidence, but each path is much more concise thanks to SOTI.
So it's a win-win situation. You get both high accuracy and low computational cost. Now, for our listeners who are thinking, okay, this is all very cool, but what does it mean for me? I think the practical implications of this research are really significant.
Absolutely. It has the potential to dramatically reduce the computational resources needed for advanced AI reasoning, which could make these technologies much more accessible and affordable.
I mean, the researchers estimate potential reductions in inference costs of 70 to 80%. That's a game changer.
Yeah, it could make it feasible to deploy sophisticated AI capabilities in resource-constrained environments, like on mobile devices or in areas with limited internet access.
So it's not just about making AI faster and cheaper. It's about making it more accessible to a wider range of people and applications. It's about democratizing access to these powerful tools.
Exactly. Now, it's important to acknowledge that, like any research, there are limitations.
Right, and the authors do address those in the paper.
They point out that they use static exemplars within each paradigm, meaning the examples were not dynamically tailored to the specific query. Also, their main evaluation was on the QL 2.5 family of models, so it's not clear yet how well these findings generalize to other AI architectures.
And they did observe some accuracy dips in highly specialized domains like medical reasoning, suggesting that there might be a need to fine-tune the approach for certain areas.
Yeah, those are valid points, but they also suggest some exciting avenues for future research.
Like what?
Well, one direction is developing dynamic exemplar selection mechanisms, potentially using techniques like retrieval augmented generation to fetch the most relevant examples for each query. They also propose creating even more specialized reasoning paradigms for different cognitive operations. And perhaps most intriguing is the idea of training reasoning models from scratch, specifically on the principles of SOTI.
So kind of building the AI reasoning engine with these efficiency principles baked in from the start.
Yeah, that could be a really interesting approach.
So to bring it all back, I think the key takeaway from our deep dive into SOT is that it represents a significant advancement in efficient AI reasoning. By taking cues from how humans think and communicate effectively, it enables AI systems to generate more focused, knowledge-driven explanations while using significantly fewer computational resources.
And for our listeners, this points to a future where AI is not just about raw power, but also about intelligent efficiency, making these incredible technologies more accessible, faster, and more cost-effective for everyone.
So here's a final thought for you to ponder. If AI continues down this path of more concise, expert-like reasoning, how might that change the way we interact with these systems? Imagine an AI that can think and communicate with the focused efficiency of a seasoned professional in any field. How would that transform the way we learn, solve problems, and collaborate with artificial intelligence? It's a fascinating question to consider. And for those who are interested in digging deeper into the technical details of SOT, the research paper and the code are publicly available on GitHub. It's a great resource for further exploration.
Definitely worth checking out.
And on that note, we'll wrap up our deep dive for today. Thanks for joining us.